Hi, I wanted to do a little review of open and short circuits. I think several of you had some issues with that on the previous test. So I wanted to kind of go over that again, and I'm going to start fairly simple and move toward more complex explanation of open and short circuits. Before we begin, though, I want you to recall your Ohm's law. And the formulas associated with that, of course, V equals voltage equals the current times the resistance. Or if we were to solve for the current in that equation, that would be the voltage divided by the resistance. And of course, the resistance would be the voltage divided by the current. So again, make sure you are familiar with Ohm's law, because that is still going to be the main equation that we're using for absolutely everything this semester. So make sure you have that committed to memory. Okay, so let's start looking at a simple circuit that just has a voltage supply of 10 volts and a resistance of 5 ohms. So we know that our current, our conventional current, will be leaving the positive terminal of our voltage source, and it will continue through the 5 ohm resistor because that's in series with the source, and it will then be returning back to the negative terminal of the voltage source. So what our circuit needs in order to create current is a voltage source where we supply this energy, and we need some resistance or some load in the circuit, and a connected pathway to get from the positive terminal back to the negative terminal. Okay, so let's use our Ohm's law and calculate what our current would be here. So we have a total voltage we're applying of 10 volts, and we have a total resistance of 5 ohms. So let me fix that. 5 ohms. So that means that we would have 2 amps of current throughout the circuit. So 2 amps coming from the source, 2 amps going through the 5 ohm resistor, 2 amps returning back to the source at the negative terminal. So the same 2 amps going through the circuit the entire time. Now, also remember that the voltage drop across that 5 ohm resistor will be the current through the 5 ohm resistor, which is the 2 amps that we just found, and the 5 ohms of resistance. So we would see that 10 volt drop from the top of the 5 ohm resistor to the bottom. And again, that is Kirchhoff's current law as well. Kirchhoff's current law basically says if we take a loop like this one and we sum the voltage rises and subtract the voltage drops, so plus 10 minus the 10 volt drop across the 5 ohm resistor, we would get 0. Okay, so that's what Kirchhoff's voltage law tells us. So again, this is a fairly simple circuit. I just wanted to start with something pretty simple so that we could then make some modifications to it and look at the short and open circuit situations as well. Okay, so let's say, what if this is, I don't know, just a simple circuit, maybe you've got a light installed, a little LED or something that you're trying to light up, and we've got this same circuit, and something happens, and let's see, I want to. Something happens, and we just kind of break the circuit in one spot. Okay, so this is what we call an open circuit. Okay, now this can happen for many reasons. Some of them we might design in the system, but let's just say this is not supposed to happen in our circuit. Let's say that maybe the light bulb becomes disconnected somehow on one side. Maybe a wire becomes loose from the power supply. It could be lots of different reasons. But whenever we have an open circuit like this, a lot of folks tend to think of electricity in terms of water flowing through pipes, and that's great, but this is kind of where the analogy falls apart, is when you have an open circuit, because if this was really water flowing through pipes, you could envision the water pouring out of one of the pipes and just never making it to the other side. And that makes sense. However, for current, this is a little bit different. For current, we really need to have this uninterrupted pathway that I'm showing you up here in the first circuit. We need that uninterrupted pathway from the positive terminal of our source back to the negative, or we won't have any current flowing. It just won't happen. So if we don't have that path, we're not going to have any current. So what happens here is we just have absolutely no current flowing from the positive terminal of the source back to the negative, zero current at all. This 10-volt source might as well just be a battery sitting in your drawer. It's not going to give you any current this way. Now, when we have an open circuit, what that means is, so if no current can jump over this gap that we have, our open circuit, then we have zero current through our 5-ohm resistor. Now, Ohm's law is still in play, okay? So if we're looking for the voltage drop across the 5-ohm resistor, that would still be given by the current through the 5-ohm resistor times the resistor value. Well, if the current is zero, then it doesn't matter what our resistor value is, the voltage drop will also be zero. Now, that does not mean, so we've got a zero voltage drop here. That's pretty easy to see. But with an open circuit, you need to remember we will have no current, but we may have voltage. I'll say maybe voltage. Okay, maybe voltage. Whoops. Okay, because what we now need to do is think about, okay, if I took a voltmeter, let's just grab our little trusty voltmeter here, and I'm going to put the black lead on one side of our open circuit. Actually, let me put the red lead there, and we'll go back and do the black lead in a minute. We'll reverse them in just a minute. So I'm going to put the red lead here. I'm going to put the black lead here. Now, at this point, there is no current flowing between where the red lead is and the black lead is in this circuit. However, there may be a difference in voltage, and here's how we're going to determine what that voltage is. So on this side, I'm going to use my highlighter here. On this side, notice that the red side of the voltmeter is connected to the positive terminal of the voltage source. So what that means is on this side, I have a plus 10 volts of voltage. That's pretty small. I'm not sure if you can see that, so let me make it a little bit bigger. Make that a little bigger. Okay, so a plus 10 volts on this side right here. Now on the other side, let's get slightly different color over here. So on this side, I'm gonna see that I'm connected to the top side of that 5-ohm resistor, but really there's no current through there, and so no voltage drop. So it's basically as if I'm connected straight to ground here. So what I would measure on this side would be the 0 volts from ground. So the voltage drop of the open circuit, let's see. Okay, let's just start that over. Here we go. Voltage drop of the open circuit. And a lot of times you'll see it even written voltage OC, or if there are points involved. For instance, if I were to name this point here A and this point here B, we would call that VAB. So the voltage drop from A to B. What that would be is the 10 volts minus the 0 volts on the other side. So 10 volts at the red lead, 0 volts at the black lead. So we would actually have 10 volts across that open circuit. So there's no current there. Okay, the open circuit current is 0, but we could have voltage here. So I just wanted to kind of make that clear about what's going on there. All right. So I want to use the same circuit, but now we're going to look at a different scenario. So I'm going to redraw the circuit over on the right-hand side here. Same circuit. Again, I'm trying to start fairly simple so that we can go on to some more complex circuits in a minute. But just want to go back over this open and short circuit idea. Now, a short circuit is a little different. A short circuit is where you might have a connection in the circuit that you don't want to have. So an open circuit is the absence of a connection where there should be some current. And a short circuit is an extra pathway for current to flow that maybe you're not intending. So let's just say something happens and we somehow get a path for current around this 5 ohm resistor. And this could be like, a stray wire that just connects two leads that you don't intend for it to do. This happens, or sometimes it could even be as simple as you have a component that malfunctions and the malfunction makes it look like a short circuit. That happens as well. So let's just do some analysis of this situation. So as you can see, if we have current that leaves the positive terminal of our source, it does have a path to get back to the negative terminal, and that's what current needs. It needs a pathway. Now you can see that we could have some current go through the 5 ohm resistor. We could have some current going through the short circuit. However, current is always going to take the path of least resistance. And when you have a path that has no resistance, all of the current is going to go that way. Okay, so when you give current a chance to escape any of the resistance, that's what you're going to have, is that the current will go all the way around and none of the current will go through the 5 ohm resistor. So right here we would have 0 amps through the 5 ohm resistor. Okay, let me rewrite that. So the resistor current would be 0 amps. However, there would be current in the circuit. Now the problem here is we don't have any resistance limiting that current anymore. So the current in this case, right here, we have a short circuit current. In this case, it's pretty much unbounded, okay? Now, what does that really mean? It means that the current from the voltage source is just going to get higher and higher and higher until a couple things could happen. It could deplete the battery voltage, the 10 volts. But what is more likely to happen is that it would get very hot and it would generate a lot of heat, because when you have unbounded current through no resistance, that's a dangerous situation. We talked about that in the early part of the semester, where if you have a 9-volt battery and you connect those two terminals together on the top accidentally, you can start a fire. And that's basically what this situation is here, is that we have nothing to bound that particular current. So in this case, what you would say is we have no current through the resistor, which also means that the voltage drop across the 5 ohm resistor, which would be the current through the 5 ohm resistor times the resistor, 0 times R. So we would have no voltage drop there. So this would be a 0 voltage drop. And again, remember our Kirchhoff's voltage law. Through this closed loop, we would need the voltage drop to be equal to the voltage rise in the circuit, and we don't have that when we have this short circuit. So that's a dangerous situation, and that's very bad. So we need the 5 ohms in the circuit to control that current. Okay, so that's the basics behind the short and open circuit. Now, I wanted to maybe give you another circuit to look at. So let's do a slightly more complicated circuit. So let's say here, well, I'll put 2 resistors in our circuit this time. And so then we'll do, let's see, 10 volts still. This time I'm going to have a 2 ohm resistor, and let's make this a 3 ohm resistor. Oh, okay. Sorry, I need to move the screen down a little so you can see that. Okay. So now let's talk about what's going on in this circuit. So first thing we're going to do is we're going to find our total resistance, RT, and the 2 ohm and the 3 ohm resistor are in series. We know that because they're connected on one side here, okay, so that the current through the 2 ohm resistor has to continue through the current of the 3 ohm resistor. So when they have the same current, we know that they're in series. Okay, so RT, to find series resistance, you would add the 2 plus 3 ohms of resistance, and we'd get a total of 5 ohms. So what that means is our current from the source would be the 10 volts divided by the 5 ohms. So we'd have 2 amps, just as in the previous example, but I've split the resistance into 2 different resistors. Okay, so we've got 2 amps here, 2 amps here, and 2 amps coming back to the negative side of the voltage source. Again, it's just a simple series circuit here. Now, let's look at our voltage drops. This is what I would call a properly working circuit. So for the voltage drop across the 2 ohm resistor, we're going to take the current through the 2 ohm resistor and multiply it by the 2 ohms. So if we have 2 amps times the 2 ohms, that means we'll have 4 volts there. And then the voltage drop across the 3 ohm resistor, we've got the current through the 3 ohm resistor times 3 ohms, not 2. Okay. 3 ohms. Okay, so we've still got 2 amps because that's in series with the source. So it is the source current going through that 3 ohm resistor. And then that means we've got a 6 volt drop there. So let me add these voltage drops. We have a 4 volt drop here, and we have a 6 volt drop here. All right, so let's look at our Kirchhoff's voltage law. Again, so looking around this loop, and I'm going to write it over here. So we've got KVL that tells us that our plus 10 volts that we apply at the source minus the 4 volts we have, that's the drop here. Okay, the 4 volts we have dropped here, minus the 6 volts across the 3 ohm resistor, that has to equal 0. And we know that it does. 10 minus 4 is 6. 6 minus 6 is 0. So that does hold up. So that's good. Now, let's talk about what happens. Again, let's have an open circuit here. Something happens, I don't know, let's say there's something wrong with the 2 ohm resistor, and there's a break on one side of it. Now, and you could even think about this, think about your Christmas lights if you use those, some of those are wired in series, and when one of the lights goes bad, the whole strand goes out. That is why. It's because they're wired in series. And so the light bulb, so this is kind of a circuit diagram symbol for a light bulb. And so what happens is when that heats up too much, the filament will break. And that is the broken part of the circuit, or that is the open circuit. Okay, so let's go back to what happens in that case. Okay, so what happens when that breaks is you no longer have a path for the current. Okay, so this 2 amps here essentially goes away. There's no current, there's no path for that current to get back to where it started. So 0 amps, 0 amps. And I think I'm just going to write over here. I'll tell you what, this over here, we're going to say this is when working correctly. Okay, I don't want to delete this on you, but I want you to understand that this is when we do not have an open or short circuit situation. All right, so let's look at now what happens when we have the open circuit situation. How does that change things? Well, again, if I sub S is 0 now because we don't have that path for current, that also means that the voltage drop across the 2 ohm resistor, the voltage drop across the 3 ohm resistor has to be 0 volts as well. If there's no current through the resistor, there can't be any voltage drop across the resistor. So I'm going to take this away as well. Let's see, take the 4 volts away, take the 6 volts away. So we don't have any voltage drop across there. Now, what would the voltage drop across the open circuit be? And I'm going to call that also AB because I'm going to make this point A, and I'm going to make this point B, okay, in the circuit. So let's just, again, imagine that you've got your voltmeter here. That's a voltmeter. So we're going to put the red lead here at A. You always want to put the red lead where you think your more positive value will be. If it's a digital multimeter, it really doesn't matter because it will just give you a negative sign if you pick the wrong side. So let's put our voltage source there, and we're just going to kind of trace through what we would expect to measure there. So the A part is connected to the positive terminal of the voltage source. So you would have 10 volts on this side, a positive 10 volts on this side. And then B is connected to through the resistor to the next resistor, and then from there all the way to ground. And that is because, remember, there's no current flowing through those resistors, which means there is no voltage drop across them. So they might as well just be wires in our circuit. So V on this side is going to show us that we're connected to ground or 10 volts. So that means when we look at our VAB, we have 10 volts at A minus 0 volts at B, or 10 volts. So our open circuit voltage would be 10 volts. We'd have 0 volts here, 0 volts here, and then, of course, we do have a voltage source, so we would have the 10 volts that you see across the open portion of our circuit. All right. Now, let's talk about what happens if we short out something in our circuit. I think I'm just going to redraw this, actually. So let's come down here, kind of redraw the same circuit. So I've got the 10 volts here, my 2 and my 3 ohm resistors. And this is probably going to be a longer video than you're used to, but you can pause it if you want to go back to it. Let's see. Okay, it's taking some time to cycle here. Let's say that instead of one of the resistors opening up or creating an open path, let's say that for some reason, maybe a mistake, maybe something else has happened in the circuit. Let's just say we've added a connection from the top to the bottom of that 3 ohm resistor. Now, again, always think about the path that you have of current from the positive terminal of your source back to the negative. Think about, kind of like a maze. How is the current going to get from the starting point to the end point? And the starting point is the positive terminal of the source, and the ending point is the negative terminal. So you want that current to have a complete path to get from the start to the finish. So I can already see that this current's going to have to go through the 2 ohm resistor. It doesn't have a choice. It's going to go straight through that 2 ohm resistor. But when it gets to this next junction here, where the 3 ohm resistor is, as you can see here, we could see some current going through the 3 ohm resistor and some current going around the 3 ohm resistor to get back to the same point. So whether the current were to go through the 3 ohm resistor or around it, it would still get back to the same point that would enable it to go back to the negative terminal of the source. Now we also know if you give current a choice, it is going to take the path of no resistance every single time. So we're not going to have any current go through the 3 ohm resistor. All of it is going to go and take this pathway around the resistor. And that's what we would call a short circuit situation. Okay, so we would say that the 3 ohm resistor is shorted out. Okay, that just means that no current's going to go through the 3 ohm resistor. It's all going to go around the 3 ohm resistor because it has a path for some reason. Maybe it's not supposed to, but it does. Okay, in this case. So what does that mean? What does that do for our, what does that do to the current? Well, as we saw in the original circuit, if it were working properly, we would have resistance of 5 ohms that would make our source current 2 amps. But in this case, we've shorted out the 3 ohm resistor, so the current is going to take this path. I'm not sure if you can see the mouse in this video, but the current's going to take the path through the 2 ohm resistor and skip over the 3 ohm resistor. So that means that the total resistance we would see, or that the total resistance the source would see, is simply the 2 ohms. It's not going to ever see the 3 ohms. So that means that our source current would be 10 volts divided by 2 ohms, and we would have 5 amps of current. So this I sub S is 5 amps. 5 amps through the 2 ohm resistor, 5 amps around the 3 ohm resistor, 5 amps back to the source. Okay. What else is going to happen here? So we will have a voltage drop across the 2 ohm resistor because we do have current there. We've got 5 amps of current there. So the voltage drop across the 2 ohm resistor would be the 5 amps times the 2 ohms, or 10 volts. We're going to have 0 volts across the 3 ohm resistor because there's no current through there. So there will be no voltage drop. So what we have here when we have shorted out the 3 ohm resistor is that we have a smaller resistance in the circuit that leads to a larger current than what we were expecting. And this is a problem because if you have, let's say your load over here, this 2 ohm resistor, or maybe it's a light or something, or a fan, maybe it's rated only to have, up to 3 amps of current. And now we've got 5. So what that means is we're probably going to burn up the component that we have left and create an open circuit after that. So it's going to continue to create problems for us probably. So anyway, so that would be the short situation. All right, so I'm going to do one more problem for you, and this time I'll try to make it a bit more complex, and I'll even maybe make it a little bit more like the bonus question that we had in the test. I think it was something a little odd like this. I'm gonna make it a little different. I'm just kind of making this up as I go. So oh, okay. Let me move this down so you can see the circuit. All right, so let's make this a 2-volt source, a 6-volt source, and I'm going to orient them in the same direction. Let's make this, I don't know, let's see, 2 ohms, 3 ohms, 3 ohms. Let's see, 4, 2, and 3. And I'm going to go ahead and name my resistors just so that we know which resistors we're talking about. Doesn't really matter how you want to name them. We're just going to make sure that they have names. All right, so let's talk about, first of all, the path for current from the positive terminal of our source to the negative terminal of our source. Now, don't worry too much about the fact that we have 2 sources right now. We'll take care of that. But let's just say each of these sources would like to push some current in that upward direction, and they would like to have current return to them from the bottom to the negative terminal. Now, is there a path for that? Well, if we have current go this way to the left, notice that we have an open circuit after the 3 ohm resistor. So there's not going to be any current in this direction. Okay, so I'm just going to get rid of that arrow. We have no current. We have no current in this pathway or on the R6 pathway. So we've got I is 0 down here as well. Okay. Again, just think about it in terms of the current needs a complete path. Otherwise, there's just not going to be any current. Can't happen. Okay, so let's look at the other side of the circuit on the right-hand side. Now, if this current were to go to the right, it would continue on through the 4 ohm resistor, continue on through the 2 ohm resistor R3, continue on through R4, which is a 3 ohm, and look right here, it does indeed get back to the circuit. Now, what I'm going to do though is I'm going to add maybe another pathway around R4 just to make it interesting and say, okay, so when the current comes to that 3 ohm resistor here, instead of going through the 3 ohm resistor, it's going to go around the 3 ohm resistor. And so I'm going to have no current there. Okay, so in this case, what I would probably do is redraw the circuit to show that path of current. So I'm going to do that maybe to the right side a little bit here. So what we're going to do is I'm going to leave off the R1 and the R6 because those have absolutely nothing to do with the current pathway. And I'm going to just kind of draw the middle here, the 2-volt source. I do have a 2 ohm resistor here. I'm going to keep that in the circuit as well. There's my 4 ohm resistor. Of course, I'm going to keep the 2 ohm resistor out here. Now for the 3, I'm going to just ignore it. I'm going to draw the path at the bottom without the resistor because the current's not going through there. And we don't really need that. So basically, here's the circuit that we have. Now, when you have voltage sources that are in series, you can combine them. So if you wanted to combine the 2 volts, why did I say 6 amps? That should be a 6 volt source. I don't know why I drew it that way. 6 volts. So when you have voltage sources in series, you would just add them. If they had been oriented the different way so that the 2 amp source was turned over, was just kind of flipped, then you would subtract the 6 volts, subtract the 2 from that, and it would be a 4 volt source. However, since they're in the same direction, that means they're both contributing to current in the same direction. They're both trying to point the current up. So that means your total voltage source, and I'm going to call it E. We tend to say total voltage is E, the voltage that we supply. That's electromotive force, so that's why. That's going to be a 6 plus 2 or an 8 volt total source. And then we have our R total. Let me move this down a little bit. We have our R total, which is going to include the 2 ohm resistance right here, plus the 4 ohm resistor right here, plus the 2 ohm resistor out here. And so our total resistance here is going to be 8 ohms. And that means that our I sub S will be 8 volts divided by 8 ohms, or 1 ampere. So I'm going to draw that in. Okay, 1 amp. So we've got 1 amp throughout here. And then I can find my voltage drops. So if I have 1 amp through the 4 ohm resistor, that's 1 times 4, which is 4 volts. And then I've got 1 amp of current through 2 ohms of resistance, so 2 volts here. And then I've got 1 amp through the 2 ohm resistor over here, so another 2 volts. So again, if we want to do our KVL, I'm going to start down here, and I'm going to add my 6, because going from the bottom to the top, we're adding that 6 volts, and then subtract my 2 volt drop across the 2 ohm resistor, add the 2 volt drop for the source, minus the 4 volts around the top, minus the 2 volts on the right hand side, and that should equal 0. So 6 minus 2 is 4, plus 2 is 6, minus 4 is 2, minus 2 is 0. Okay, so that checks out. And that's actually what's going on in the circuit. Okay, so let's go back to our original drawing and fill in some of this. So remember, we have, and I'm just going to write in, I think, the voltages for right now. So we know we've got a 2 volt drop here. Let me get rid of. We've got a 2 volt drop here. We've got a 4 volt drop here. Another 2 volt drop here. Remember, we've got 0 volt drop across our 3 ohm resistor. So if we make this our ground node, this whole node is connected to 0 volts. Okay, that's what our ground node is. It's our reference node. Okay, so what if I were to ask you what the voltage drop would be? Let's say we were going to measure it out here at this open circuit. So we have our red lead here at the top and our black lead down here. Well, let's trace and figure out what our voltage is at those points. So first of all, let's look over here. Okay, so what would our voltage drop be up here? Well, again, we've got our 0 volts down here. I'm going to start at ground. And then when we add our 6 volts to it, we would be at a plus 6 volt level here. Actually, I think I drew the plus and the minus wrong here. I did. That's a drop. So when we have the current entering the resistor on this bottom side, that means our voltage is more positive on that side than on the side where the current leaves. So that's actually a -2. I just draw the plus and minus wrong for some reason. So the plus 6 volts on this bottom side minus the 2 volts means we're at a +4 now. Okay. It's going to take some time for that to refresh and get up on the screen. Hopefully that happens soon. I'm not seeing it come up on the video. Hello. Okay. Maybe it'll come to us in a minute. I'm trying to refresh here. And then on the other side of the resistor, we've got another 2 volts we're adding. So if we added 2 volts to the 4, we would be at a +6 volts. I'm not seeing why this is not refreshing for me here. Oh, I have a spinning wheel. Let's see if we can sync a little bit better. Let's see. Not seeing what's going on here. Let me see if no, I'm still on the Wi-Fi. Oh, there it is. It came up. Okay, just took a minute, didn't it? Okay, so we've got our 6 volts up here that we traced from the ground. So that means that on the top side of our voltmeter, we have a +6 volts. And on the bottom side, of course, we have 0 volts because we've connected that to ground. So our voltmeter, our open circuit voltage up here, VOC, is 6 minus 0, or 6 volts. And again, there's a lot of other measurements we could make in here. But again, a couple tips when you're looking at open and short circuits. First of all, you always want to start with tracing the path of the current through the circuit that we have, which is what we did in our circuit here. So we looked at the fact that we want our current to come from the positive terminal of the source, and it needs to come back to the negative terminal. So we're looking for how to connect that up. And of course, we found that there was a path on this right-hand side here that would go through R2, R3. It would actually go around the 3 ohm resistor R4, but then it would make it back to the 6 volt source, which would then make it back to the 2 volt source. So you always want to start with tracing the path of current, and then redraw the circuit to match what that looks like. Okay, so I'm hoping this helped a little bit with your circuit analysis with the open and short circuits, and let me know if you have any questions.